So before I continue that discussion, I want to just refresh your mind about the important concepts, and you will hear again and again. I'm assuming most of you are familiar with, like supervised learning, which is you have labels, and labels typically are by humans, which is harder. Self-supervised learning does not need labels, and zero-shot learning, you don't have to do training. You just use that pre-trained network to solve the problem. Few-shot learning, where you have few examples, not too many, and you can fine-tune and run your network. Then we have the pre-trained wise fine-tune model. So you will see in these figures the pre-trained model is called frozen. When we build this thing, it will be shown by snowflakes, and the fine-tuning will be like a flame. It will be burning. So we will do that, and then you will hear again image encoder, because we are talking about visual language models. So there'll be visual part, will be image encoder, and as you will see, most of the time we are using VIT clip. So VIT is transformer and it's pre-trained on a clip model, and there are different versions. There's some public clips, some proprietary clips, like OpenAI clip is still not out, but people have reproduced very close to what they have. Similarly, text encoder. So we have to have text encoder, and BERT we talk about is one, and T5, there are many other ones you will hear. So then there's a large language model, GPT, Vicuna, OPT, Llama, and there are many of those, right? So just get familiar, feel comfortable with those. Then important thing in deep learning is data sets, right? So in particular, the image and text pairs, because deep learning revolution started with the ImageNet data set, which was 1,000 classes, and for each of them we have examples, and it demonstrated deep learning really works. Now for this visual language model, starting with CLIP, image text pair is important because you are bringing in the language to the computer vision. So, there are lots of data set. The original image text pair, which was the clip, OpenAI clip was trained, it's not still out, it's a private. Okay, so, but there are lots of publicly available data set. People are, using that, and it's billions of, the number of image text pairs. So other important concepts of loss or objective function, and we have gone through, we'll look at more contrastive loss, which that's what we use clip, and captioning loss, that you have an image, and then you want to produce a captions, and you want to train so that the captions output is close to the ground truth. Image text matching, and then there are many tasks that once you train the visual language model, then you can do many tasks, right? So that's why they are called also foundational models. So when you want to recognize, like ImageNet, or the action recognition, like Kinetic and so on, so most of them are accuracy. How many times you can do correctly recognize particular image or particular video. Retrieval is also a very good task in visual language model. So you have text to image retrieval or image to text retrieval. So given a text phrase, you want to find out which is relevant image in the whole data set. And similarly, given the image, you want to find out what's the relevant text or caption for that. So for that is recall, how well you can recall, and that's a metric. Then VQA, visual question answering, that given a question, what's your answer? And again, the ground truth answer, how well you are doing, what's your accuracy. And then captioning, you have the ground truth captions, and you have the caption from the network, and you want to compare these text, and there are several different metrics for that. So other important concept is open source versus proprietary, that can be data, or also it can be model, okay? So as I mentioned, the CLIP originally trained, that data set is still not public, and but there are some other public data sets. And the models also open, CLIP from OpenAI is not open, not available. But people have, reading the papers and so on, they produce a model which performance is close to what the actual open is. So this whole there's discussion. If you guys follow the Twitter, Jan LeCun, who is the kind of father of the deep learning, got a Turing Award with Hinton and Joshua Benjo. He has been pushing this that everything should be open. And Meta, that he works for Meta is for it, but OpenAI is not. And there's all this, discussion going back and forth and so on. Of course, OpenAI is the nonprofit, and there's a whole thing about that. Okay, so let's now go through. We talk about CoK, which was the contrastive and captioning loss. Poly we talk about, and now we are going to talk about FLAMINGO, FLAVA, Painter, and then BLIP-2, image bind, language bind, Lava, and video ChatGPT. So let's get started with FLAMINGO. So this is a visual language model for few-shot learning. And so in this one, as I said, there's this notation. So this blue one is a pre-trained and frozen. We are not going to touch upon that. And then the other one we will train from scratch or fine-tune. So what we are going to do in Fleming, we will have, say, two images, image on left and image on right, and we will encode. And this typical encoder will be, clip encoder, image encoder, VIT. And similarly, we will take the second image, we'll use same encoder and get the tokens out of that. Now here I'm showing twice, but actually it's the same encoder. It's just sharing of the parameters. So now we get tokens from these vision encoder. Then we have perceiver resampler, which will take the tokens and reduce the number of tokens. As you know, the image is, big resolution, simple 200 by 212 by 200 image will have about 200 tokens. But text typically don't have that many tokens. So since the visual language model, so we want to reduce the number of tokens. So one simple way, we just drop some tokens, but that's not good. So there's this old paper perceiver, which will come up optimal way to come up starting from, say, 200 tokens will give you, say, 50 tokens and so on. So there's a whole paper we discussed, in Transformer class a couple of years ago. We have presentation on YouTube. If you are interested to learn perceiver, you can do that. So that's again the point about the research is there's no one answer like I cover here, everything. Research is exploration, right? So you will read one paper, then you will have to read other papers from that say, well, in order to understand that, I have to read this one. In order to understand this, I will read this. So once you exhaust that, then you will have knowledge about this sub area. Then you can produce new work and come up with novel work and creative work. And then you can become the leader in the field. Because once you do PhD, the day you do the defense, you are the best person in that area. You are the most knowledgeable person. Okay, that's why you're called doctor. Okay, so that's what we are aiming for. So this is perceiver. And so then we will have the visual encoder. So again, this is a text. This is a very cute dog. And this caption for the other one is probably this cute cat. And then go to the text encoder. And now here is the kind of integration of the vision and the text, image and text. So this thing, what we have is the different layers of the LLM. Okay, so these are the first layer of the large language model and second one so on end. And then we have these gated X attention layers. where we are going to do cross attention between the image input and the text input. We talk about cross attention transformers, basic idea. And that's the way we will combine. Then after that, we will get the output from the last block of the large language model, which will say a very serious game. Okay, so that's it. So now, and that's a presentation if you want to find out more about about the perceiver. Okay, so now let's go a little bit detailed. So what we have here is the X, which is the vision input, and then we have the language input, and what we will do cross attention. So the key and value will be from vision, and the query will be from language, and we'll do cross attention. Then we have some getting, then feed forward, then getting, and self attention, feed forward, and that's it. So that will keep repeating that. And that's it. That is your Flamingo model. Okay. So now it uses this 70 billion chinchilla language model. That's another large language model. And it uses ResNet vision encoder. Objective is that given the up to LH token of the text and the image, we want to predict the next token, the LH token. Okay, and this is up, less than L, so up to say L minus 1 tokens of text, and the image we want to predict the LH token. So we will kind of maximize this probability as we'll compare with the ground truth. So that's our objective. Okay. So in this one, they train this on a mix of vision and language data sets. So they look at this interleaved multimodal massive website, 43 million web pages. And then they also look at the pairs of image and video text. And one is called LTIP, and which consists of 312 million image and text pairs. Others called VTIP, which consists of 27 million short videos, about 22 seconds on the average with sentences. So that's their data set. So about a data set, that's very, very important. So one of the project you guys can think about, these groups, can be actually build a new data set which is needed, especially instruction tuning data set. And that'll be a build project. Whereas as I mentioned before, that you can write a paper in URIPS and data set. There's a data set track because it requires a lot of effort, manual effort, at the same time some nice, elegant way to have these different number of steps to start with the data which is available, which is errors, and do semi-automated way to improve the data set. Because you can come up with automated way or human annotated, but you need a combination of that if you want to do millions of these. So, keep in mind if you want to work on some project related to that. Okay, so now given that you can do this. So you give one image, this is chinchilla. They are mainly found in Chile. This is Shibu. They are popular in Japan. Then it is asking, what is this? And then system is going to tell you a flamingo. They are found in the Caribbean and South America. It's pretty amazing, right? Computer is able to do that. And you know how it works. It's very nice. So it's a power of the large language model and the visual, input that we can do that. And there are many other examples. What is the title of this painting? Answer the hallucination, turbot, or whatever. Where is this painting displayed? Answer this. What is the name of the city where this paint was painted? So that's in France, or this. I don't know which this painting is from Van Gogh or something. I don't know. Okay, so something like that, these kind of examples you can do. Also, you can do this one, conversation. So this is picture of teddy bears on the moon. This is what Flamingo is saying. Then user is asking what are they doing. They are having conversation. Then what objects are they using? It looks like computer. Is this surprising? Yes, it is surprising. Why is the picture surprising to you? I think it's surprising because teddy bears are not usually found on the moon. And like this, what is common? You give three images. About these three images, they are all flamingos and so on. So you can do all those interesting things. Of course, this is an apple with a sticker on it. What does the sticker say? It says iPod. So it's able to read also the text, OCR. Where's the photo taken? It looks taken backyard. Do you think it's a printed or handwritten? It looks like it's handwritten. What color is this a sticker? It's white. It's pretty impressive, right? So we can do that. And so on. So of course in these things you will find there'll be errors, and that's what even large language model want to call hallucination, right? They will just make up. So the question is that there will be hallucination or incorrect things in the visual language model also. But if you're using two modalities, then maybe there's a way to actually, reduce the hallucination, because if they have to agree, both models have to agree and so on. That's kind of my hypothesis. Okay, so they show pretty impressive results. And these are the several tasks, I think 16 tasks or something. And so they compare with the fully supervised other methods compared to their method, which is the few shots, 32 shots. Once they train that, then uh, on the sixth task, they surpass. As you see, all these are more than 100% is fully supervised. Okay. Then on these other tasks, they compare with a zero shot and or few shot, they also beat all those. Okay, so that's their score with the red, and this one is their state of art. So which is very good, because in order to get a paper accepted, you have to show that it really works on these things, and that's what you're going to show in your project term paper. Okay, so then we go to FLAVA. This is a foundational language and visual alignment model. So the idea here is that we will have the multimodal, unimodal training, pre-training. We'll have image and text pairs, unpaired images, unpaired text, and this model will build. And once it's built, then we can do visual recognition, like an ImageNet. We can do language understanding, anything. They have a whole set of tasks called Blue. And we can do multimodal reasoning like VQA. So the good thing about this is that this model is trained on fully, all the data set are openly available. So you can get all those, because that is one advantage, right? And when you want to build AI system, then you want to verify, you want to check it out, so you can do that. But if the proprietary data set is very difficult to replicate, and you just have to rely on them, and there's this problem. So one thing, as you know, that many researchers sign later that we should stop doing this research in this AI, because it's dangerous. AI will take over the world, and humans will be slave and so on. So I mean, it's not going to happen. So I haven't signed the letter, but so main thing, these people um, who are for the open source are saying that, well, we don't have to worry about uh, any threat to humanity, but we do need to be careful about what the systems are capable of doing. And if they are open source, then anybody can check, right? And that's the motivation of this whole movement to make everything open source. Okay, so now they use these data sets for which are publicly available. So they have 70 million image and text pairs, and average length about 12 words. And with that, now how the system works, also very intuitive, very simple. So you have input image and you do image encoder. So you have all these page, tokens. Each page is a token, and then you will have, you can do with vision tasks, without like ImageNet task and vision taskets. Then you have also text, and then you have text tokens, text encoder, and then you can do whatever NLP task, whatever you want to. So now main thing here is this multimodal encoder. So you take these image encoder tokens and text encoder tokens and you put in here, and then this encoder is trained with this VQA or other multimodal tasks, helpful memes and so on. So that is FLAVA system. It's a multimodal. And now if you look at in more detail, so we have mask image modeling is one loss. So we will take an image, mask some of the patches, and we'll try to reconstruct like MA mask autoencoder I showed you other day. It's pretty simple, pretty intuitive and works so well. So this is one loss they're going to use for this one, mask image modeling. Okay. Similarly, you can use the same thing for language. Now here you are going to mask the language tokens. Okay. So then other loss they are using the image text matching. So you have an image and you have corresponding text. If they match, just say 1. If they don't match, 0, just binary. Then you have the mask multimodal modeling, where you're going to actually mask these or this multimodal encoder. You are going to mask whether text or images, and you'll have this that lost. Then you have a global contrastive loss. Okay, so very similar to the CLIP loss what we have been talking about. So all these losses are used to train this, and then it works pretty well. So now FLAVA versus CLIP. So on the green one is FLAVA, which is doing better on many of the tasks. Of course, it doesn't do all the tasks. And the left side, the blue one, is, CLIP is doing better. So that's why it's minus. So that's your FLAVA. Okay. So let's look at this paper called Painter. So this is also very interesting. And so it is like in context learning. So you have some context and rapidly you can adapt a model to many different tasks. Okay. Now is a journals model, and it's image centric. Everything you want to solve is based on images. Input is the image, output is the image. Okay. So basically you are given an input image, you want in Paint the desired missing output image. Okay. That's why it's called Painter, Paint. So they use the, again, VIT large. And you can see that, the reason I cover VIT, the second lecture, that's a foundation. So you need to be very clear, and the clip that I covered, because also you will see clip again and again. So that's very important. So again, VIT is large, huge, and all those tiny and so on. And then they are using the loss is just the L1 loss, the absolute value after what's predicted and what is the ground truth. Okay, so this here we have. So we have, say, image and corresponding output, and this is the prompt. Okay, this we know the output of this image. Now we want a painter to give in a new image and give us output. So these are the different tasks. This is semantic segmentation. Okay, so the painter, this network, will give you semantic segmentation of this image. Then this one is instant segmentation. So instant segmentation like a semantic segmentation, but because this animal is the same, it appears twice. So we need to, separate that. And this one is a depth estimation. Given an image, we want to estimate the depth 3D. So again, we give it this. That's why it's in context learning, right? We tell it that, well, this is the image and this is the depth. Now I give you this image, tell me the depth, and tells you this one. Okay. So then we have key point detection. This image, these are key point join angles, and we want to get the key point for this one. Okay. Then we have denoising. This image is, not that clear, then we denoise. Similarly, now we give this image and give you better image, much better than this one. And keep going. This denaming is remove the rain kind of thing. So it looks much better here as compared to what we input. So it was completely dark. Now we can see the thing. And this is image enhancement. You can see nothing, but here this you can improve. This works for the categories for which trained. Now it will work also open category. It hasn't been trained for this category. So again, this object segmentation, key point detection, is a segmentation. So okay. So now how they do that, because it's pretty nice, right? If you can do that, pretty interesting. And the method is very, very simple, very intuitive. And the idea is that you have these image pairs, right? I showed you that this is the image and this is semantic segmentation. This is image, this is segmentation on different tasks, insert segmentation and all those things. So they will select two pairs like this and put them in one image. These two will be in one image, the input image, and this will be another image. And they will do these patches. So now in this one, the result one, they will mask these patches. Okay. Then they will have this vision transformer. It will determine those masks, so apply the image mask image encoder, auto encoder, right? So so that's it. And so the main thing is that how do you come up with this kind of formulation, right? This is first time to use the knowledge you have, use the transformer and other thing, and solve something interesting problem. So they have lots of very good results. This is on different data set, as you see here, that this is the test image and prediction and the ground truth. It's very close. Test image, prediction, ground truth. And the depth one, this is the instant segmentation. This is, pose, the key points and denoising and so on. So, so that's it. Now let's talk about next one. Yes, please.
You're doing like instant segmentation with it? Is it actually like result in class data? Like, does it know that all horses are horses, or like could you extract that from the result?
Say it again.
Like if you're doing the instance segmentation,
yes,
is it just trying to color it as close as you can, or does it like, are the colors significant enough where you look at that image, you could be like, this horse is a horse at this
yeah,
location?
okay. So instant segmentation means that you are able to say this is a horse, but there are two horses, then you need to use a different color for each. So you're counting, right?
Yeah.
So that's the reason they are showing the different colors. Is that what you're asking? Or?
I'm just asking, like, if you're using a, like, it's doing a mask that looks like how an instant segmentation mask would be.
Mm-hmm.
But if I'm using instant segmentation, I get like data for each instance, like where it's located and what class and stuff. I was wondering if like the colors, like, is it just trying to make it look like the other thing, or is there actual data?
No, it is true. See, as I told you that this is you can compare with the ground truth that's doing the right thing. And I think you are asking how it's trained. Is that what you're asking? Like you take these and you mask these tokens, patches, and and then you predict those tokens. Is that your question? Because I'm confused what you're asking.
So
Do you understand the question? Yeah. Yeah.
So like I've used Detectron too.
Yeah.
And
Will detect objects and so on. Yes.
And that's an instance segmentation model.
Yeah.
And when a result is going to be the image, it's going to have the mask like that, but it's also going to have data for each instance. So
Yeah,
I'm
yeah.
asking, like, if that returns stuff like that,
yeah,
like,
this
is it saying like does it?
Yes, yeah, okay, I understand. Yeah, so see, this is an image. So this has all the data which Detectron will give you, because you know that this particular one is one object because of one color. So it's a fine segmentation. All the pixels which have this color, that's one object. Then green one is another object, and in this case, these are different objects. So they go through in the paper in detail, if you are interested, how to formulate all these problems in the image in, image out. So that's yes. So you can get exactly same output what specialized intersegmentation method will give you. This will give you that. Okay. Yeah. There was one question there.
Could you maybe go back on that?
Yeah.
So if I heard correctly, the objective was to like take an image pair as input, and then you're given one more image, and like you have to do the transformation that the input pair did, right?
Yeah, it's not a transformation.
The input pair was the input pair. They had two images. The first one was doing some transformation and giving another image, right?
Yeah, I mean, you want is a transformation. So see that, let's look at this image, right? So this is the semantic segmentation of this image, which means every pixel at different color, different time. So this is another example. Again, semantic segmentation of this is this, okay? So now we have these two examples, okay? So what we are doing that now we are learning that how we can, if the some of these pages we mask out, then we ask the transformer to predict, learn the transformer so that it outputs. These are the ground truth. This is what predict compare. So it will learn to predict those mask tokens, right? That's the idea here. Now what we are going to do when we do the testing. So actually, as I showed you here, when we do testing, we'll mask all the tokens. Then it will predict the whole thing, which is amazing, right?
Yeah, because it's not exactly learning what kind of transformation the.
No, there's no, don't keep saying transformation. There's no transformation here. This is the understanding. Given an image, we want to do semantic segmentation. Semantic segmentation means each pixel we want to assign the label. That is this the road? Is it the building? Is it a tree? That's called semantic segmentation. Yes. So there are methods, as you said, Detectron will do that. There are many methods. So that's first thing. Now, what we have converted this thing is that we can solve that problem and many other problems using this painter. And it's very intuitive that we give, image and its output. Then we give a new image. We want to find out the semantic segmentation and what's the way we want to do it, the way it's learned, that we mask out the pages and predict that. Now during testing, we mask out all of them and it's going to predict that. That's pretty nice. Yes.
So for Painter, if the training is only on purely image train, like we're not providing any sort of class information. Like for example, in the instance and in semantic, we're just providing like the visualization of the mask. So like after we get out for semantic segmentation or instance segmentation, while we're getting out masks that show individual objects on like outline, we're not given any sort of classification of each individual object.
Yeah, yeah, that's a good question. So see that if you read the paper in detail, so they talk about how you can take the classical definition of semantic segmentation, convert that to the image in, image out. How you take the key point detection, for example, you will have an XY location of little join. So they are talking about, say, let's convert all that to just an image, and they define. They talk about that, and you can look at it. But right now we are saying, well, all the tasks we can say input is image, output is image. And this is all, whatever it's giving you, it is with any specialized method will give you that.
Okay.
It's a equivalent. It's exact. Okay.
I
Okay.
have one more question.
Yeah.
So in this case, none of the tasks can be zero sum probably, right?
None of what?
None of the tasks can be zero sum, right? And you can't do zero sum learning here, right?
Yeah, I mean, there's nothing. We have the, in this case, we have one, let's see, one example here, right? In context learning. So we have one example here. So you can say that this is one shot, right? So given this one, we can predict that. But the thing about that is it can not only do one thing, but it can do all those things. So it's not to look at zero shot or one shot. It's in context learning that we tell it, well, this is input, this should be output. Now this is input, what should be the output? So it's figuring out. It's very interesting, right? That's the way you learn. Okay. Yes. Okay. Yeah. Repeat. What's the question? Can you guys unmute and ask a question, please?
For my understanding, Dr. Shah, is there multiple task heads, or is this model using an auto-regressive method for each task?
Yeah, that's a very good question. And actually, no, there is no multiple head. That's it. This is what we have. So that's the beauty of this, that if you wanted to solve all these different problems, then you need to have many heads. But here is the image in, image out. That's it. So you are able to do all those things, same network, which will do all those. Now, the question is, when you take the, like key point detection, then you have to prepare that input image, prepare their output image, and interpretation of that. What does that mean? Because here, you're saying these are the key point, and each of the key point has different color, and maybe the green one is the left shoulder, the red one is the right shoulder, and so on. So yeah, there's no multiple heads. Yes.
So question for like depth estimation, right? Those those pixel values are going to be a lot different than the RGB values of the input task prompts.
Yes.
So it will give that same range, or is it just going to be some kind of grayscale value or some float value?
Good question. Yeah. So they have talked about the paper, they normalize, but what you get is that real depth map. Depth map will be the one you give as input, like this is the example. If this is a depth map of this, what it give you, this is a depth map of this. So they take care of this normalization, all this thing. So you can, read the more details.
Oh, wow.
Okay, so let's quickly just cover one more thing, then we can stop. Okay, so BLIP-2, this is very important paper, okay? BLIP-2 is used a lot, and I think this will be one of the paper that you will do replication. And so, listen to carefully. And this is open source, from this Salesforce. Okay, so it's called bootstrapping language model pre-training with frozen image encoders and large language models. Okay, so this is a very different way, and it's pretty interesting. So you're talking about detectron, then there is a dater. You know about dater? Dater is the transformer-based object detector. Yeah, so so this using some of the ideas from there. Okay, so you have image encoder. Okay, so it's frozen. It can be clip kind of thing. Now, what they are doing here, they are learning the queries. Queries are just these vectors, and they will initialize randomly, but queries will extract the useful information or images, which will go to the language model. Okay, and the way these will be learned is called Q-former. Q-former is a very interesting concept, so you want to listen very carefully. Okay, so so once we get the queries, which extract the useful information from an image based on the text input. But the image is a lot of things, right? So we want to, extract information from image based on a text, and then we send that to the large language model. We can do useful things. So that's a basic idea here. Then we will go in detail. Okay. So this is the Q former. So we take input image. Again, we do the pages and tokens. And this works. This is your Q former. So what we are going to do, that we will take this number of queries and we will randomly initialize them. Okay. So then we will have self-attention and cross-attention. And similarly, with the image, we'll have the inputted text, and we'll encode that, and we will get the text tokens. And now, after the self-attention, we will do cross-attention between the image and the text, and the feed forward, and similarly feed forward. So we have these two, as you've been seeing, the text encoder, image encoder. Okay, so let's go in detail, a little bit detail. So now, one last, we will do image and text matching. So we'll say this image as a text matching, say 1. If it's not matching, 0, just binary. Now, for that last, the attention we are going to use, because this is, the cross attention, are going to use, we are going to explain that. And so here we have two kinds of tokens, right? So we have the text tokens, and we have the query tokens. These are the query tokens. And text token will come from here, and then image tokens and so on. So now image and text matching. So we have, say, query tokens. Just example, there are 2 query tokens, and there are 2 text tokens. So now, when the empty square, all these are unmasked. So this will be bidirectional self-attention mask, which means each of the query token will be attended by both query tokens and both text tokens. And similarly, each of the text token will be attended with all the query tokens are called text tokens. So it's all bidirectional, it's all attention. Okay, so that's for the image text matching. Then we have another loss, image text contrastive loss. Okay, that's very similar to your clip loss. So for that one, we are going to use this multimodal causal self-attention. Okay, so again, we have 2 query tokens, text tokens. So now for these 2 query tokens, they will not get attention from text. Okay, so they'll mask. And for the text token, so the first text token will get attention from itself, but will not get attention from the second token because it hasn't seen that. Okay, so that's why it's causal. The second text token will get attention from itself, which is second token, and also from previous one. So that's why it's called causal. So that's the way they are using this cross attention. Then we have a third loss, which is image grounded text generation, because we are going to ask, given the image, given the learned queries, given the text, then we'll generate a text. Okay, so for that one, we are going to use the unimodal self-attention. So query tokens will attend to itself, text token will attend to itself, but they won't be, attention from query to text and text to query. So that's what they are using. And that's it. So once you can do that, and they use again the image model VIT large 14, and there's another VIT giant 14 from EvaClip, and LLM they are using OPT or decoder model, FLAN T5 for the encoder model, and dataset 129 million images in total. COCO, visual genome, these are all data sets, C3M, CC12M, and so on. LON, 400 million. And then they use these synthetic captions to improve the captions. And that's one thing. BLIP-2 is known for. Okay, so once you have trained the Q-farmer, again, Q-farmer is interesting concept. It extracts the useful information from the image based on a text. Yes, and so you query. That's why it's called query token. You query the image, what it should give you, which is relevant, and you get this out, and that goes to the fully connected. Then that goes to the LLM decoder. So as you know, that LLM can be decoder only, or it can be encoder decoder. So GPT is decoder only, and some other ones are encoder decoder, but mostly a decoder only. So they show that this will work for the encoder decoder or only decoder. And these kind of things you can do. Explain the advantage of this product, it goes through that. Tell me something about this history of this place, like that. Then you can do conversation and all those things. This photo, unusual. How could someone get out of house, and amazing things. So these are the results. So I told you what FLAMINGO, um, 10 billion model. It's not open source. That's what DeepMind, Google, and BLIP-2 is open source, only 188 million, but they can beat that. Visual question answering, image captioning, image text retrieval. So that's what we have. This I should. Okay, so shall we do one more? I think we still have 10 minutes, right? What do you think? 5 minutes. Oh, this is, huh? Yeah, let's ask questions. Okay, more questions from audience.
So for BLIP-2,
Yeah.
as I understood the definition of bootstrapping, it's supposed to be sampling with replacement. Is bootstrapping here being used under a different definition?
Bootstrapping is that, see, you already have image encoders, right?
Yes.
Which you want to improve. You start with that and you want to improve that. And that's what this Q-farmer is. It's improving the image representation as compared. You could have used directly the image encoder, right? Yes. But here you are getting better information because you have these learnable queries and they're combining text. Okay. Are you happy?
I mean, from the answer you give me, the answer is no, they're not using what I was traditionally taught as definition of bootstrapping. So,
I don't know what the traditional definition of bootstrapping.
When I taught bootstrapping, when I was taught, it was
so that is, yeah. So in the paper they say the bootstrap is not that bootstrap. It's the bootstrap what the dictionary meaning is.
Oh
yeah, dictionary for what you know when you write on house. That's okay. Yeah, don't look into it.
It's not literal.
Serious. Okay, go ahead.
Like for the results page and how it's performed better for question and answering. The example previous to this, like previous with the sunset, I don't understand how like you could say it's logical or not, because in my opinion, like the previous example with the sunset, it's illogical. Like the I don't know. I think this is before this. Yeah, this one. If you continue, like the output is illogical. Like love is like a sunset. It's hard to see it coming. Like that's not logical. Like we know when the sunset's gonna happen, So like for accuracy reasons and like results at the end, who says this is logical or not? Or are we just saying like, oh, it gives us an answer that's somewhat right?
Very good question. So see, the whole thing now is how you evaluate these large language models or visual language models. So that's a huge issue. And they are relying on these old data sets. All these data sets were before LLM. People have been doing that. So they are relying, and metrics are old. So there'll be a huge research to come up with the better evaluation metrics, better data sets. Of course, I mean, humans don't agree. right? Not humans don't agree on everything, right? It's a subjective. So that's matter is also there. But yeah, it's all these things right now they are providing numbers based on the ground truth data set, whatever that is. And there may be errors. Okay. Yeah. Okay, so just 1 second. There's a question from the which virtual class. Can you unmute and ask the question, please?
So Dr. Shah, how does a cross-attention layer differ from a masked self-attentional layer? And why wouldn't we want to just pass encoded image tokens into the self-attention layer in the beginning of the model alongside the text?
The difference between cross-attention and the self-attention?
Well, the masked self-attention.
Did you understand what I'm saying?
He's saying how does cross-attention differ from a masked self-attention? So basically that caption generation, we're doing some masking.
Yeah, so okay, so first is, cross attention is different from mask attention, right? From self attention, right? Self attention, all query Q value are from same thing. Cross attention, they are two different things, right? So that's clear. Now you are talking about this thing, the how this, maybe I should. Okay, so first one was the bidirectional self-attention mask. And then we have image text contrastive mask. And then we have image, the uni-model self-attention mask. So what's your question again?
So why wouldn't we want to input the image encoded tokens into the self-attention layer and use additional masks as opposed to using a cross-attention layer after the self-attention?
You mean here the self-attention, then we have, after that we have class attention, something, these two? Yeah. Self-attention you always can use, right, to improve your thing. The self-attention, we talk about that, you have some input and you want to make it better so that you can look at all the tokens and get a support that this token, how much support it has from all the other tokens. So you get attention matrix and you multiply, you get a better improvement, concurrence, and long-term context and so on. Self-attention is always good. So that's, as we use in VIT and so on, we are doing self-attention. Now, the main thing here is a cross-attention, because we are doing the cross-attention between the image and the text. And that's the most interesting thing. Okay? Okay. So who else? There was somebody else. Yeah.
Is there like a metric to measure robustness of the large language model?
Yeah. There are some metrics, but they're very initial, and they are being developed, and there's a whole analysis on the limitation of visual language model. There was a nice paper, I think, a couple of weeks ago, and we will discuss that. Eyes wide shut. So that's a paper. They show how limited the visual language models are right now. You take two images, exactly same, not much different, but their embedding is different. Or two images very different, but the embedding is same. So there's a lot of issues. So that's kind of hottest topic to determine how to measure these, how good these models are and so on, because it gets into subjective things, right? It's a conversation, how you people talk to each other and how do you measure that? Okay, so any last question?
Dr. Shah, I did have like one general question.
Yes.
Just kind of about transformer architectures and like just in general, not necessarily this one. You were talking about how these were trained off of just kind of a conglomerate of a bunch of different data sets. And I was just wondering, do these models still fall short in terms of like class imbalance data sets? That's obviously class imbalance isn't quite the word I'm looking for because these are text image pairs. But for example, if we have, a picture like our data set is skewed towards dogs versus cats, are the output probabilities going to be skewed as well for these? If that makes sense.
I think that's a good question, and class imbalance is always there. That's why they want to, generate billions of these.
Yeah.
These data sets are so large,
Just
so
lose it in the
billions of data
conglomerate.
set, and then there is now language. It's not like a classes, right? That's one major difference. So you can imagine it, 1,000 classes is airplane, but airplane, is not enough. Airplane can have many text pairs, right? The airplane image and background and all those things. So I think the general view is if you have as large as possible data set, larger the better.
Okay, thank you.
Now, if it is cleaner, if there are a lot of errors, where there's a whole world, people clean up these captions and so on. If it's a clean data set, larger data set, larger model, then those models will perform well. So that's the idea. But yeah, there will be all kinds of issues. But if there's many of those, and in a way, as you see, we are not talking about the way these systems are trained, networks are trained. There's no classification error, right? So this is the error contrastive learning.
Yeah, and I'm not sure like what kind of metric you would even use to measure that for text image pairs. But
yeah, so it's just the best will be the humans, right?
yeah.
And a human won't agree, right? So human can have captions, and you can maybe ask 5 people on Mechanical Turk and get agreements on. So it's a pretty complex problem. One last question. Yeah.
This is more in general on video models. I noticed on many of the results they give like the number of parameters in millions for each model. Is that including both the frozen image encoder and whatever large language model they're including into the overall architecture, or is that purely on the trainable parameters that they're giving us?
I think it's mostly trainable parameters. What do you think? Yeah. Yeah. Okay, very good. So nice discussion, good question. So we'll end here, and I will see you guys next week. Okay, bye.